My first example with finding the area of a parallelogram may have been a little too simple to follow some of the details of computing a cross product, since there were so many zeros and the non-zero components were all positive. So I wanted to work through another example all three ways, where we have all non-zero entries. Doesn't matter what they are, just want to make them different. So I took 1, 2, 3, 4, 5, 6, and just for fun, made the first component here negative, so that we have a negative entry floating around, and you can see, certain places where you have to be careful about signs. So let's suppose we have this cross product of these two vectors, negative 1, 2, 3, crossed with 4, 5, 6, and we want to compute that. Again, I'll show all three techniques, starting with the one in the textbook using the method of cofactor expansion. We begin by writing a 3x3 matrix in air quotes, where it is, again, debatable whether this actually qualifies as a matrix or whatever, but we'll not worry about that. We have this 3x3 array of values, and we can use cofactor expansion. So we'll start with I, and again, we imagine deleting the first row and the first column, the row and column containing I. When we do that, we're left with this matrix 2, 3, 5, 6. So we have I times the determinant of 2, 3, 5, 6. There is an alternating plus minus plus pattern. So we have minus j times the determinant of, now focusing on j, imagine removing the row and column containing j. That leaves us with negative 1, 3, 4, 6. And finally, we have plus k. We're on to k. We imagine removing that row and column. So we have the determinant of negative 1, 2, 4, 5. All right. Do remember that the cross product is not commutative. It is anti-commutative. So you always want to put your first vector before your second vector. It does matter. Your ijk go on top. The next row should be your first vector, and then the last row should be your second vector. But once you've set those up and gone through all of this, now we see that we have I hat times, again, the product of the main diagonal, that's 2 times 6, minus the product of the back diagonal, 3 times 5, minus j times the product of the main diagonal. I don't really need parentheses there, that's fine. Product of the main diagonal, negative 1 times 6, minus the product of the back diagonal, that's 3 times 4, plus k times negative 1 times 5, minus 2 times 4. So we have 12 minus 15 I minus negative 6 minus 12 j plus negative 5 minus 8 k, assuming I have done all of that quick mental arithmetic correctly. 12 minus 15 leaves us a negative 3i. Negative 6 minus 12, we have a negative 18, but that is subtraction there, so that is plus 18j. Negative 5 minus 8 looks like a negative 13k. So this appears to be the vector in question. This is an ijk form, which is a perfectly acceptable way to leave it. I believe I stated it in angle bracket form with the components. Yeah. So if you do want to translate it back to angle brackets, you can certainly do so as negative 3, 18, negative 13. So that would be another way of writing this answer. All right. So this is using cofactor expansion, writing out all the steps. If we consider the same problem with rule of Saros, it starts off the same way. We construct the exact same matrix. Then we recopy the first couple columns. And now we consider these forward diagonals, right? We have I times 2 times 6, that is 12i. We have j times 3 times 4, that is 12j. We have k times negative 1 times 5, that is negative 5k. For the back diagonals, we need the diagonals that are a full 3 terms. So we have k times 2 times 4 gives us 8k. I keep forgetting my hats and my k's. I times 3 times 5 is 15i. And j times negative 1 times 6 is negative 6j. Those are just a bunch of little notations here. So again, we take the sum of the forward diagonal entries minus the sum of the back diagonal entries. So you notice this minus here because we have the negative 6j, right? And you can collect these directly, right? You can take a 12i minus 15i, you have your 12j minus negative 6j. You might find it easier to reduce the chances of sign errors if you distribute that negative through, or not, you don't need to. If you want to group them this way, you certainly can, and leave them like that. Or you can push the negative through. Which I mentioned this in passing on my previous example. Instead of writing the forward products summed as a group minus a group with the backward products, what many students will do is just copy the forward products and then do minus each of these. So you have 12i plus 12j minus 5k, and then come back and say minus 8k minus 15i minus the negative makes plus 6j. So you can basically skip this step right here and jump straight to this one. If you prefer to do that, that's probably faster. You might find that to be easier. And then it's a matter of collecting like terms, right? We have 12i minus 15i is negative 3i. We have 12j plus 6j gives us plus 18j. And minus 5k minus 8k looks like negative 13k. And let me check. That should be 3i plus 18j minus 13k. 3i plus 18j plus minus 13k, yes. The same result we got last time. I was just checking against any possible errors in arithmetic or copying, sign errors, that kind of thing. And again, as before, you can turn that into the angle bracket notation. Okay. Now these are the two most common bookkeeping methods for keeping track of this. It's also possible, once you've practiced with these, you can combine them in various ways as long as you are careful and consistent and you know exactly what you're doing, right? So just as an example, I've been doing these for quite some time. I say as I miswrite something. It's what happens when you try to say one thing while writing another. But when looking at something like this, again, I've been doing these a long time, so what I would probably do is I would often say, okay, we want our I component. We get the I by looking at this. So we have 2 times 6 is 12, minus 3 times 5 is 15. J, and this is kind of using, sort of using something like Rule of Saros or something like a reversed. What I'm doing here mentally is kind of a blend of the two, but I know that I can just take the 3 times 4, giving me the 12, minus negative 1 times 6 is negative 6, so that becomes plus 6. And then for the k, I see that we have this minor here, so I have negative 1 times 5, minus 4 times 2, so I have that, and then simplify. So, once you've done a bunch of these, as usual, do not push things faster than you're ready for them, right? I know there's a temptation. Believe me, I'm a mathematician. Mathematicians are famously lazy. We try to do as much work as possible. Well, we try to accomplish as much as possible with as little work as possible. Start off by writing all of the steps, and then you will discover for yourself which steps you do need and which steps don't help you at all. Only skip a step if you are certain that it does not help you at all. If it will not help you to write something down, then you can probably skip it. Unless you would be skipping so many things that somebody else would not be able to follow your work. Right? You want to make sure that peers, colleagues, bosses, underlings, or graders can tell what your thought process is and follow what you're doing to be convinced that your answer is indeed correct. So you need to show enough of your work to make it clear that you know what's going on and to leave a record of what you've done. Also keep in mind, as any of you who have done any computer programming know, the importance of commenting code. When we talk about making things easy for somebody else reading your work, after enough time has passed, your future self will count as a different person. When you come back and say at the end of the semester when you're preparing for the final exam and you're looking over your old notes, if you skip too many steps, when you're looking over your old notes, you might not remember what on earth you were doing. So it is surprising how different our mindsets can become after just a month or two. So do make sure to leave enough of a sketch, both for other people and for your future self, as to how these things are working out. As far as the last method here, again, just to illustrate the technique that I wrote up in that other document I posted online that makes use of the algebraic properties of these. 4i plus 5j. The first step is to write these in ijk notation if they are not already done so. Now this one, the previous two methods, I wrote pretty much all of the details. I'm not going to do that here because if you read that document, you see that writing every single little detail along the way is quite cumbersome indeed. But with just a little bit of practice, you can pretty quickly, easily do these things. The idea is that we're doing the full double distribution here. It's like FOIL, but with more terms. So we start with this negative I. We want to distribute that over each term here. I cross I is 0, so that term drops out entirely. So we have negative I times 5j. Negative 1 times 5 is negative 5. And I cross j, if I said times the first time, I meant cross. So negative I cross 5j. The scalars, negative 1 times 5, negative 5. And then I cross j is k, following that alphabetic cycle that I described in the, in the article there. We have I to j to k and back to I. There's this ijk, ijk, ijk cycle that you go through. So that's this. When we take negative I crossed with 6k, we have negative 1 times 6 is negative 6. And I cross k is going backwards, so that gives us a negative j. That'll flip the sign and make that plus 6j. So that takes care of that. Now we distribute the 2j. 2j cross 4i. 2 times 4 is 8. And j cross I, again, is going in reverse alphabetical order. J cross I is negative k, so that becomes a minus 8k. That's why I left that blank. I didn't write that plus up front. J cross j is 0, so we can drop that term. We have 2j cross 6k. 2 times 6 is 12. J cross k, I, j, k, I, that's alphabetical order. We get j cross k is I, so we have plus 12i. So that takes care of distributing that. Now finally we have this 3k. 3k cross 4i, 3 times 4 is 12. K cross I is j, so that's plus 12j. 3k cross 5j, 3 times 5 is 15. K cross j is going backwards, that's negative I. And 3k cross 6k, well, k cross k is 0. So we leave that out. Now we need to collect like terms. We have 12i and negative 15i. Those combine to make negative 3i. Looking at the j's, we have 6j plus 12j is plus 18j. And now we have negative 5k minus 8k is negative 13k. And I believe that's the same as what we had before. Negative 3, 18, negative 13, negative 3, 18, negative 13. There we go. Okay. So again, with some practice, all three methods are roughly comparable in the amount of work involved. There's a little bit more writing out of work with the algebraic notation, but you're skipping the initial setup of having to write up that whole 3x3 determinant, which you kind of need to do in either of the first two methods, right? Even when you shortcut things, there isn't really a way around arranging things this way because it's very dependent upon the two-dimensional arrangement of all of the vectors and components, whereas this is just algebra. You can kind of organize things however you want. But yeah, that was a quick run through of doing the same problem with more differences so that hopefully you could track through better which numbers were going where. And those three methods, make sure not to cross them over, right? You will probably want to try each of them first and see which ones you like, which one you like best. For most students, there's one that just feels the easiest for the way you think and the way you work. And then mainly practice that one. And along the way, maybe practice some of the others. But first, make sure you probably want to first, whichever one works best for you, practice that one the most first until you have it mastered, because you don't want to get interference from the others once you've decided that those don't work as well. Once you have mastered that one and there's no danger of forgetting how to take cross products with your preferred method, then maybe practice the other two, because it is sometimes nice to have those in your back pocket. I've mentioned in particular, as we saw in the example with the parallelogram, if a lot of components are 0, then the algebraic method is really quick and easy if you're practiced with that. So it's nice to have that ready to pull out in a pinch, but not necessary. You never actually need this method. You can always do cross products with any of the three methods. No one of them will ever actually be required. Just at least one of them, your pick. So I hope that helps.